Okay, so let's do an advanced problem to practice our problem solving skills using everything that we've learned so far. Let's read the problem together. A tank of gas is 82% argon gas by mass. If the tank weighs 3.0 times 10 to the fourth kilograms, how many atoms of argon gas are present in the tank? So we want to understand the problem. There's a lot of things that we can do to try to better understand the problem. Sometimes it's drawing a picture. Sometimes you're going to be able to understand the problem right off the bat, and you may feel comfortable just skipping this step. One of my favorite things to do is draw a picture. I tend to be a visual learner sometimes, and it helps me. Sometimes it helps to just reword the problem. And that's actually what we sometimes do in step 2. Steps 1 and step 2 are sometimes one and the same. So you probably will approach these steps differently depending on the problem. Let's draw a picture for this problem. Let's do a rectangular tank. And we know that 82% of the mass of this tank is argon gas. So we have a tank, and within our tank we have atoms of argon. We know that this argon is 82% of the mass, and that everything else is 100 minus 82, right? So that's 18% of mass. And I didn't put an A in my mass here. There we go, mass. Right? And what we want to know is how many atoms is this? That helps me understand the problem better, personally. You're going to find different strategies that are going to help you understand the problem. Okay? And we can talk more about that as we do more examples. So how can we simplify this problem? I personally find simplifying the problem most helpful by making the wording condensed and writing it out as shorthand as possible and putting it into words that we discuss more simply in class. You know, we've learned different types of problems, and we use different language to describe those problems. So what I would say is, you know what? What kind of problems do I have to do that I've learned about in this class in order to solve the problem? That's going to help me simplify this problem. So what I'm looking at is that I have a percentage and I have mass. And if I have mass of argon and I have to go to atoms of argon, it looks to me like I've got to do some some calculations with moles, right? Because I'm going to need to use Avogadro's number. I'm going to need to get the mass from the periodic table. So I'm going to need to do a mass to mole calculation, and then a mole to gram atom calculation. But I also have a percent here, right? So I first need to find out the mass from the percent, it looks like. I know the total mass, right? So I need to first find the mass of argon atoms using the percent, and then I can do a mass to atoms conversion. So that's what I'm going to say. I'm going to simplify that in words. First, find the mass of atoms, of argon, mass of argon, then convert to atoms. Wow, isn't that much more simple? It kind of tells me more straightforward what I need to do. First, find the mass of argon, then convert to atoms. Okay, well that's a little much more simpler. And that's why we do these, use these problem-solving strategies, because if I understand the problem a little bit better by looking at it, then I'm able to simplify the wording and give myself a better sense of what I'm supposed to do. Okay, so what is our next step? Our next step is to organize what I know. Well, if we look back at the problem, I know that the tank's mass is 3.0 times 10 to the 4th kilograms. All right, tank mass. I know the percentage of the mass that is argon. Which equals 82%, right? And that's really basically what I know from the problem, right? So that step is pretty simple, okay? Now, we don't necessarily want to stop there. It's good to put as much information in here as possible. And so what we can do is we can carry over our information if we want to. And that is, we can copy our simplified problem, because that helps us, that is information we know, right? And so I want to copy that. What did I just do? I'm going to paste it. And that's because it's information I know. It's what I know I need to do. So I know, well, I didn't copy it all. Let's just write it. First, find the mass of argon. Then convert to atoms. Okay. So, now that we have everything down we know, we need to state what we need to know, right? Well, what do I need to know? Well, in order to solve this problem, what I need to know is what the fraction of the total mass is, because that will be my actual number of atoms, right? So I need to know and that's just saying what the mass of argon is, right? I need to know the mass of argon atoms. I'm sorry, the mass of argon, which is saying the same thing, in the tank. What do I also need to know? I need to know my metric prefix conversion, right? Things I need to remember. For kilograms to grams, right? Now, if I'm going to convert from grams to atoms, I'm going to need the periodic table. Why do I need the periodic table? Remember, I need the periodic table for the molar mass. Remember, the molar mass of argon, which is grams of argon for every 1 mole of argon. If I'm going to do my symbol, I need to do it right. Capital A, R. I need to know that 1 mole of argon equals what? Avogadro's number. 6.022 times 10 to the 23rd atoms of argon. These are all the things that I need to know to be successful in my problem. And this is what I meant when I talked about in the former slide how we're going to take all the information that we've learned and put it together in order to form a strategy. Okay? All right, so now that we've listed everything we need to know, we can use this information to make a plan. Okay? All right, we've kind of essentially done that, right? Now, the question is, what kind of plan? And this actually ties back into what we need to know. We need to know dimensional analysis. Some of this stuff is a little redundant, but it helps writing it out. We also need to know sig figs and the math associated with it, right? We need to know our scientific notation. Math. Okay. So, things that we're all going to use in the problem. And this is all helping us make our plan. Because what are we going to use? We're going to use dimensional analysis to solve this problem. There's one more thing that we need to know how to do, and that is to take a percent. And we've already learned how to do this in our average atomic mass. Take a percent of a mass. All right? So that's going to be our first step. Find the mass of argon using the percent given by multiplying the percent by the tank's total mass. That's step one, right? That will give us our mass of argon. Gives mass of argon. But what does that give it to us in? That will give it to us in kilograms, right? Because the total mass was in kilograms. In kilograms. So then we need to do what? If we have the mass of argon, we can do mass to moles and moles to atoms. But it's in kilograms, so we need to convert the mass using dimensional analysis. Now I'm going to put under here, we'll need our metric prefixes. That was the kilogram to gram. We'll need to use scientific notation. We need to remember to use sig figs. All right? And that will all come together to give us our answer. We've made our plan. Okay? Now we carry it out. All right, so we go back and we say, okay, well, I need to find the mass of argon by using the percent given. That percent, I believe, was 82. Let's check it. Yeah, 82. All right. So if it's a percent, it's out of 100, right? So 82 out of 100 equals 0.82. And then we need to multiply that by the mass, right? Which I'm just going to check it. 3.0 times 10 to the 4 kilograms. And so let's do our math. Remember sig figs. Got 2 here, 2 here. That means I'll have 2. We're not going to round to the end of this problem, so we're just going to keep track without a line. And that's going to be what? Kilograms of argon. All right, we move to the next step. Convert mass using dimensional analysis. So we're going to convert the mass to atoms, right? So we've done starting and going. Where am I starting? I'm starting with kilograms, and I'm going all the way to atoms. To get there, I need to first go to grams, Then I need to go to moles. Then I go to atoms, right? All right. Well, how do we get from kilograms to grams? I know that 1 kilogram equals 10 to the 3 grams, right? Well, I'm going to need my periodic table for argon. So I'm going to look it up on my periodic table. Let's see, do I have one inside here? I should have an existing periodic table in my files. And I do. So I'm going to pull one up here. And argon. Here's what we're going to need for going from grams to moles, right? Oh, that is blurry. There we go. So, grams to moles is our next, right? So how many grams are in 1 mole? Well, that's the atomic mass, right? Or the molar mass. 39.948 grams equal 1 mole for argon. How do we get from moles to atoms? 1 mole equals 6.022 times 10 to the 23rd. All right? All right. Oh dear. All right, let's ditch our periodic table down here. So, let's do this. 2.46 times 10 to the 4 kilograms of argon. Kilograms of argon has to go on the bottom to cancel out. Where's our conversion factor with that? It's right here, kilograms. 1 kilogram of argon must go to 10 to the 3rd grams. All right, this is where we stop, and I remind you of something very important. There was a significant digits rule, counting rule, that we learned a way back that we haven't really applied much yet. What we want to remember is that when we're counting significant digits, there's a rule where some significant digits have infinite number of significant digits. I'm sorry, some numbers have an infinite number of significant digits. One of those are conversion factors, some conversion factors, not all conversion factors, some conversion factors. When we're doing conversion factors like metric prefixes, these have infinite numbers of significant digits because they're what we call perfect numbers, right? We know that 1 perfect kilogram has 10 to the 3 perfect grams in it. So we consider these to be infinitely significant because we're not going to write out 1.000 all the way to infinity. We can't do that on a piece of paper. And so that symbol there, a sideways 8, means infinite. And so I always mark those so I don't count them when I'm doing my significant digits. I know this number had 2. Okay, so that's what that means. We go to our next conversion factor. Grams is going to go on the bottom, and that's of argon. Where's that conversion factor? It's here. It's my molar mass, 39.948. And that's in 1 mole. Now, when we get our molar mass on our periodic table, remember that's saying in a perfect mole. So this mole here is a counting number. It's an infinite number of significant digits. This number down here was gotten in AMUs. It was determined by scientists doing calculations. That is not infinite. Okay? So it always has significant digits. Next conversion factor will be our last. This is the one that scientists came up with. 1 mole The idea of the mole is an counting number. It's infinite. However, the number we came up with was scientifically determined. 6.022 times 10 to the 23rd atoms of argon. So it has significant digits. And remember, we said we were going to use 4 sig figs always in this class. Okay. I should always write out all my units. Make sure everything cancels. So checking that I set it up right. It does. So now we'll do our math to the proper number of significant digits. .46 times 6.022, and then that gets divided by 39.948. That gives me 0.3708, and that's going to be to 2 significant digits, right? This is my least number. So I'll draw my line there, and we can't forget about our exponents. I'm going to have 4 plus 23 on the top, so that's plus 4 there, and then that's it. There's no, I can't forget about my 3, plus 3. So 4 plus 3 is 7, so that's going to equal 30. So this will be times 10 to the 30, no scientific notation on the bottom. Atoms of argon. Now we round and put this in proper scientific notation. The 7 goes to the 0, we keep it the same. And then proper scientific notation, this decimal will go to the right by 1, so we'll reduce by 1, so this will be a 29. And our final answer is 3.7 times 10 to the 29 argon atoms. Now scientists can do further calculations, knowing exactly how many chemical reactions they can do with that amount of argon inside the tank. They can go on to do further and use it for further information that they need for their chemistry. Okay, so that's how we use these problem-solving strategies, okay? Some of these things that we do using these problem strategies may seem a little bit overkill for this problem, okay? This was a little bit more of a simple problem, okay? But some of the problems that we're going to encounter will be much more involved and more complex, and we will really be utilizing some of these steps much more so than others, okay? For example, I went a little overkill here, okay? I wrote out, we'll need to know our dimensional analysis, our sig figs. And some of you might be like, okay, yeah, of course, Mr. G. Yeah, we're going to need that. I need to write it down. I understand that, okay? But some of us may not have, we might not be there, and that's okay. We're all going to be at different stages with this, all right? But it is very important that we have a strategy and we know how to work through these step by step, because our brains just might not be there yet and be able to just look at these problems and be able to just, bam, know what to do, okay? Working through them in a stepwise fashion helps us get to the right answer. Okay, let's look at another problem. It might seem like a step up in difficulty when you read it, but really, it's actually kind of easier. But you'll be surprised at what your mind can do when you read a problem. So let's read it. Just like atoms, entire molecules that are combinations of atoms can have a molar mass as well. So a biochemist is trying to synthesize antibodies for a vaccine for the virus. I meant to say the coronavirus. The antibodies have a molecular mass of 47 kilograms per mole, since they're much larger than an actual element or an atom. The antibodies are 66.0% carbon by mole, not by mass. What percent by mole are the other atoms in the antibody? So when you read the problem, you're like, holy crap, I'm not ready for this, right? Oh my God, what's going on here? Talking about antibodies and vaccines, and I know nothing about all this. Well, you don't need to know anything about that. And that's where your mind can take over. Remember, we talked about the emotional brain and the rational brain. Problems like these are where your emotional brain can sometimes take over and leave aside your rational brain and let fear get the most of you. And this is where we want to really let step 1 and step 2 do the dirty work. Okay? And this is why problem solving strategies are so important. We want to focus on the parts of the problem that we actually know about, because the rest of it is a little bit of a distraction. Okay? So let's talk about understanding the problem. Let's read. It says, just like atoms. We know about atoms. We learned about atoms. Entire molecules that are combinations of atoms can have a molar mass. We learned about molar mass. We know what molar mass is. So let's try to understand it. Okay? It says entire molecules that are combinations of atoms. I think here it would be helpful to draw a picture. If a molecule is a combination of atoms, why don't we just draw a big chunk of atoms to help us get started? This will help us start to understand the problem. Now, it talks about later in the problem how 66% of this big molecule is carbon. Let's draw some different atoms in there, using different colors. Let's use some glue for other atoms. Who cares if we're drawing the right proportions? Alright, we got a big chunk of atoms in there, right? We'll call that a molecule. Okay, so that's a good start to trying to understand this. So it says, just like atoms, entire molecules. We have our entire molecule. It's a combination of atoms, and it can have a molar mass. So what it seems like the problem is telling us is that this whole thing can have that idea, that concept of a molar mass, which, remember, molar mass, let's write it out. Molar mass is the mass in grams, at least on the periodic table, that equals 1 mole of the substance. Which also equals 6.022 times 10 to the 23rd, at least for what we've learned, atoms of the substance, right? Because the substance was always an element, right? But we also learned that a mole can be anything, right? A mole, we could have a mole of elephants, we can have a mole of couches. Well, this is a mole of molecules, right? Well, so we should probably start thinking a little differently. If this has a molar mass and it's a molecule, it's 1 mole. We could think of it as 1 mole of molecule of the substance, which would mean 1 mole of the molecule of the substance equals 6.22 times 10 to the 23rd molecules instead of atoms, right? All right. Oops, I erased some of my picture. Okay. And it looks like it's giving us kilograms per mole. Well, why not? Why can't it be kilograms per mole? I mean, it's just saying that it's the mass per mole. We just learned about the periodic table part for atoms. Red is fine, I guess. Alright, so a biochemist is trying to synthesize antibodies for a vaccine for the virus, coronavirus. So we know what the molecular... so they're even calling it molecular mass. The molecular mass. So when it's a molecule, it's called molecular mass. "47 grams of it are 1 mole of it." So 47, or kilograms. So 47 kilograms of this equals 1 mole of this, which should equal, based on what we said over here, 6.022 times 10 to the 23rd molecules of it. Okay. Now, it says that the antibodies are 66% carbon by mole, not mass. So maybe we should do that in our picture. We should say, go down here and say, not 66% of the kilograms, big X, but in 1 mole, if this represents 1 mole, then it's 66% of the mole. Okay. 0.0. Sig figs always matter. Okay. Now we need to know what percent by mole are the other atoms. So everything else. Okay. Wow. We just went through all of that. This is not so hard, right? So, let's see if we can simplify this into words. If 1 mole of a molecule of an antibody because we care about the mole part, right? It's like it's saying way more information than we need, right? Because we don't care about the mass. If 1 mole of a molecule of an antibody is 66.0 percent carbon, what percent of the mole are the other atoms in the mole of the molecule? Okay. Well, geez. If we understand the problem and we simplify it, geez, that doesn't seem so hard to me. Okay, let's go to our next step. What do we organize what we know? We know that 1 mole of the molecule has 66.0% carbon. And since we simplified the problem, we don't need to write information that we know that we don't need to know. Right? I mean, why write out stuff that is irrelevant? That's why this step is so important. And you've learned in math class, there's always, sometimes in word problems, irrelevant information. Right? Organize what we know. We want to know the remaining percent that is the other atoms. In 1 mole. What do we need to know? How to subtract. That's what I'm going to say. And spell. Right? I mean, all we got to do is subtract, right? What do we have to subtract? From 100. We need to know sig fig math. Always. Better do your sig fig math. I mean, for a problem that is now this easy, once we've gotten down to the details, we wouldn't want to mess it up with significant digit math. Okay, so let's make our plane. Subtract. Can't spell subtract. Subtract 66.0% from 100%. And let's carry it out. Now we know this is a perfect 100%, right? 100% of the atoms in that molecule is a perfect 100%. Subtract 66.0. So since this is a perfect 100, we can imagine this being dot 0, 0, 0, always to infinity. So when we draw our vertical line, it's going to be here. Okay, and so 38.0%. Oh, not 38. Jeez. Not on my A game today. 34%. Okay? Checking ourselves would just be to add 34 to 66 to get 100. So 34% of the rest of the atoms in that molecule are going to be, in that 1 mole, are going to be the other atoms that compose it, right? So why do I give you that problem? Because I want you to really take my advice and not skip these steps, okay? Because you could really do yourself a disservice by looking at a problem and just saying that sounds too hard, when really it is so easy, okay? Now, there are some problems. I'm going to give you some problems that do require you to really go the distance, okay? Because there are problems that are very challenging, and we have to know how to do them, you know. But there are problems that are also very easy. There's a whole gambit of types of problems in this class. But one of the things that we are, one of the goals of chemistry is to learn critical thinking skills and problem solving skills. Okay. We've learned from our first unit that in the nature of science, that science is about, it's a rigorous process in the scientific method where we go through steps of testing and retesting, and that requires problem solving. We need to be able to design challenges that test different problems, and we need to be able to work through different strategies. And if one fails, then we need to be able to evaluate why it failed, and that includes our own failures. Okay, so if we don't do a problem right, we need to have a strategy to use to check why we didn't do it right and be able to reevaluate it. And it's important to have a strategy that we follow so that we have the tools to go back and reevaluate and rethink. Okay? And this is why we use these skills and I teach these skills. Okay? So not so bad, right? All right. All right, so let's do our final advanced problem solving example. This one's a little bit more challenging. When I say challenging, usually what that means simply is that there's just more steps involved and it's a little bit more tedious. If you know the information in the class and you know how to do all the problems, these advanced problems just involve more steps. They involve you to have to put the pieces together, and that's what these problem solving strategies help you do. So let's do it, and you'll see what I mean. So here's the problem. I'll switch to a different view here. An alien spaceship arrives on Earth carrying a virus that starts infecting humans. Scientists identify the virus to have a new element. After enough analysis, the element seems to have 2 isotopes. It's ET324 with a percent abundance of 88.32%, a mass of 323.9887 AMUs. Isotope ET325 with a percent abundance of 11.68%, mass 324.7661 AMUs. It's critical for the scientists to determine a certain reaction containing this element. They must obtain 424 milligrams of the element ET, aka extraterrestrium, to do this reaction. If they have isolated 1.23 times 10 to the 12 atoms, do they have enough to do the reaction? All right. Well, like we've done in the last two problems, what we want to do first is understand the problem. What's going on so that we have the big picture, okay? So we know that we've got this new element. We're given information on the isotopes that make up the element. Okay, information like we've seen before to solve for average atomic mass. And it seems like they don't give us the average atomic mass. So that should be a big hint here, okay? And then we skip straight to a scenario where we have this reaction that they need a certain amount of this element for. And we know that they need a certain number of atoms, and we want to know, based on that number of atoms, if they have enough, given that they need a certain number of milligrams. Okay, so atoms, mass. Okay, I think I see the big picture here. But let's start out with some things. We learned in our average atomic mass lesson that sometimes working backwards is a good strategy. And so that's what I'm going to approach this at. So I know that they're asking us, bottom line here, if they have isolated this many atoms, do they have enough to do the reaction? Well, they need this many milligrams. So it would seem to me that we need to go and figure out how many milligrams that this many atoms is, right? So if we know how many milligrams this many atoms are, we can compare it to this much and see if they have what they need. So this tells me that we need to do an atoms to milligrams conversion, or an atoms to mass conversion, right? Okay, so that I understand that. So I don't need to draw a picture really, but I can write out that. Ooh, I'm in purple. Oops, previous problem. Get in black here. I need to do an atoms to mass in milligrams conversion. So those are my mole conversions, right? And that's using the element extraterrestrium. And are we gonna find that on the periodic table? No, I mean, we just told them that this is a new element. And since we can't find that on the periodic table using mole conversions, we know that one of our conversion factors is the molar mass, right? And where do we get that? That's from the average atomic mass, right? So that's why they're working backwards kind of helps us here. So we know we need to solve then for the average atomic mass. For extraterrestrium. All right, now we can simplify the problem. So solve for ET's average atomic mass. Do it in steps. In step 2, convert from atoms of ET to milligrams of ET and compare to needed amount. Of ET to see if they can save the world. This is a crazy problem. All right. So, let's move to our next step and list what we know. All right. So, organize what we know. So, we know our isotopic data for ET. Sometimes it's helpful to just like move it over, and just depends on how you're writing out on your page. I'm not going to rewrite all the isotopic data. So we need to know our isotopic data. We know, gosh, that's about, we know we need, how many milligrams was that? 424 milligrams. Of ET. All right? That's about all we really know from the problem. What do we need to know? Well, we need to know the average atomic mass of ET. We need to know milligram, nope, that would be megagram. Oh. Milligram to gram conversion factor. For that, we need to know our mole conversion factors. Which, of course, one of them is this. The other is Avogadro's number. We need to know scientific notation math. Sig figs. Dimensional analysis. We need to know, I'm just going to group it with this. The average atomic mass, we need to know the process of solving. And I think I've covered it all. All right. Now we've got all the pieces. We need to make a plan, right? So, we move forward. So, since we need our average atomic mass to do anything, we first need to turn percent abundance into decimal form. And we need to multiply those each by their respective mass numbers. Right? Now remember, once we have that, we need to take the product of those and add them up. And all the while, keep track of sig figs. And And keep track of sig figs. Am I missing something? And not round to the end. Don't round until the end. Right? Okay, so, and that provides us with our atomic mass. Now, we have the average atomic mass, but what we really got out of this was the ET's molar mass. Right? How many grams per mole? Now we use dimensional analysis to convert from atoms of ET to moles of ET to grams of ET to milligrams of ET. Step 3, I'm going to say sig figs. I mean, and the reason sig figs are so important is because you never know how close we're going to be. Like, we could be off by like one sig fig, and sig figs are going to matter here, right? Could be the difference between one sig fig as to whether we have enough or not. I don't know. I just made up this problem. I just picked some random number of atoms, and I have no idea how close we're going to be. We could be super close, we could be really far off. I have no idea. All right, and then, then compare to quantity needed. I'm anxious. I want to know if we're going to save the world or not. All right, now we carry it out. All right, so what are our percent abundances times our masses? Let's go back to step. All right, so 88.32 and 11.68. All right, decimal form, right? Oh, shoot. All right. Sure, my decimals are clearly where they're supposed to be. Forget the isotopes. They were 324 and 325. All right, we multiply those by the masses. Holy cow. 3239887. 3239887. 3247661. AMUs, we can leave off that since it's not going to matter. Okay, now we do our multiplication. So 0.8832 times 323.9887 gives me 286.14682.1168 times 324.7661, 37.9326.805. Sig figs. This has got 4, this has got 4, and these have more. So we know we're going to go to 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so vertical line here. So we add those to 86.14.682. Well, that's not right. I need to do that again. 286.14.682 plus 37.9326. All right, 324.0795. All right, now we got our final answer is 324.1 grams per mole for ET. Now, that's well and good, but that's not the number we're going to use because we don't ever round to the very end of our problem, right? So we're going to use this with its extra digits in our conversion. Okay. Now we do our step 2. See what I mean by just being tedious? It's just long. Use dimensional analysis to convert from atoms. So we got to figure out what our atoms were. We had 1.23 times 10 to the 12. 1.23 times 10 to the 12 atoms of ET times, how do we go from atoms to moles, as our problem says, our steps say? We do atoms of ET in the denominator, because it has to cancel out. 6.022 times 10 to the 23, right? Avogadro's number, that is a 3, not a 2. Dang it. 23. So 1 mole. Remember, that is an infinite sig fig there. We do not count it because it's a perfect 1. All right, next we have 1 mole on top. Whoops. So 1 mole must go on the bottom. Another infinite sig fig, and that's moles of ET. What are we trying to get to? We're trying to get to all the way to milligrams. So next we can go to grams, right? Because we have solved for the average atomic mass, which is the molar mass now. So now we can use the number we just solved. 324.0795, the one with all the digits, but keep track of sig figs. 1, 2, 3, 4 sig figs. And that is grams of ET. All right, we don't want grams, you want milligrams. We have to compare it. So now grams goes in the bottom, grams of ET, and milligrams of ET, finally. Now, this is where we got to remember our metric prefixes. We know that there's 10 to the 3 milligrams in 1 gram. Now, again, let's make sure where we have our perfect sig figs so we don't mess up sig figs. And got 3 here, 4, 4. We're going to have 3 sig figs in our final answer. Okay, so let's simplify our expression here. We're going to multiply 1.23 times 324.0795. We're going to divide that by 6.022. I get 66.19. I can stop there since I'm rounding to 3 sig figs. Let's not forget our exponents. I've got 12 plus 3, that's 15 minus 23. 15. Oh, that's not my pen. 15. Let's do a different color. 15 minus 23 equals -8 times 10 to the -8 milligrams. All right, proper scientific notation. Take that over 1. Left, larger, bring that up. -7. Rounding this off at this point here goes up. So our final answer is 6.62 times 10 to the -7 milligrams of ET. Should put that there. Compare. Not done yet. What did we need? We needed 424. We're screwed. We're all dead. Scientists need to get to work and isolate some more of that extraterrestrium, I think, before we all die. All right, guys. So have some, make sure you take breaks when you're doing these problems. Don't give up, okay? The way I describe this portion of our class, our course, I should say, is like a roller coaster, okay? So where we start out, we start out, and our class goes like this. Then we get to this point here, and we go, whoa, gets easier and easier and easier, levels out. Yeah, it's not so bad. Okay, I'll show you where we're at. We're like right here. Okay, we're like right here. So stick with it. All right. We have the beginning. I have a tough job because I have the beginning to get you prepared for all the stuff, all the math and all the problem solving skills that are necessary for us to do all the actual chemistry. Right? This is like reactions, chemical reactions. Here we talk about like what we call thermodynamics, bonding of chemicals. Reactions is the biggest one. Thermodynamics, bonding, electrochemistry, the periodic table, gases. There's so much chemistry that we have, but you got to have the skills to do it all. Okay? So we're getting all of those skills under our belt so that we can actually do chemistry. So keep with it. Keep on trucking along. I mean, I'm not saying that once you get to this point that this all goes away. I'm saying you got to get it all under your belt, and it's hard and it's tough. But once you get it all under your belt and smooth sailing and it all becomes second nature to you, then it's like smooth sailing. We got a little hump in here. We have to learn this thing called stoichiometry, but it's basically the principles that we all learn in here with a couple new conversion factors. So that's why it's just a tiny little hump. Okay, it's not bad. All right, so stick with it. I'll give you some practice problems so you can get those skills down like normal. And as always, ask for help if you need it. Sign up for office hours. Peace.